Do you feel the vibes?
Let's talk about vertical and horizontal asymptotes today. So, vertical asymptotes. So x equals a, right? Vertical line x equals a is a vertical asymptote if either the limit of f of x as x approaches a from the positive side is plus or minus infinity, or the limit of f of x as x approaches a from the negative side is plus or minus infinity. So that's how mathematically we say that something is a vertical asymptote, right? So if the graph as x approaches a, approaches positive or negative infinity, then it's a vertical asymptote. And this could be a vertical asymptote even if the graph approaches positive or negative infinity from one side, right? Like this is enough to say that there is a vertical asymptote there, right? So for example, if you have, like a logarithm, like a, graph of ln of x, right? Looks like this. There is a vertical asymptote here, right? That's only as x approaches 0 from the positive side, right? This is negative infinity. So it's enough for it to be a vertical asymptote. Now, sometimes you also have, another portion from the other side, right? And that's fine as well. Okay, that's why it's either. Right, so here, find the vertical asymptotes of this graph, then describe the behavior to the left and right of each vertical asymptote. Right, so we know that if you have the equation of a graph, it will be a vertical asymptote if there is a point that makes the denominator 0, right? Now, the denominator is 0 at points where there is any discontinuity. But remember, if the term in the denominator cancels with the numerator, then it's a removable discontinuity. When it does not cancel, it's an infinite discontinuity or a vertical asymptote. So here, there is a vertical asymptote at x equals -2, right? So let's describe the behavior to the left and right of each vertical asymptote. So we say the limit of f of x as x approaches -2 from the minus side is what? And then the limit of f of x as x approaches to -2 from the plus side is what? So, you can do this in, however way you want. You don't have to sketch a graph, right? Or you can, just to give you like another, like a diagram or something, Okay, so -2, right? The left side of -2 is like -2.1, 2.2, -3, and so on. So for those values, look here, this is always going to be positive, correct? Because when you square that, figure that -1 is positive. So now this is where we need to look at. So let's say you were at like -2.5. This denominator will be a negative value, correct? So then you say this is negative infinity. Now, if you want to sketch something, just to, have you like, grounded, you can do that as well, right? And so here, it's going to go down. Now, to the right of -2, this is like, -1.9, -1.5, -1, and so on. Numerator is still always positive, but here, how much would that be? The denominator on the other side, huh? Positive, right? So this will be positive infinity, or dne. Now, hang on. Another way that you could have done that is using multiplicity, because we know then at x equals negative 2, this denominator has a multiplicity of 1, which is odd. So if it's negative on one side of it, it's got to change sign to the other. Okay? So this is where everything that you learned, right, is something in your like back pocket that you can just take out and use, right? Okay, so let's take a look at this one. Let's factor, right? How does this factor? 3 here, negative, plus 1. Is that right? Yep. Okay, so there are definitely vertical asymptotes at x equals negative a half and at x equals 3. So at x equals negative a half, we want to describe the behavior, right, from the left and from the right. So limit of f of x as x approaches negative a half from the minus side, limit of f of x as x approaches negative a half from the plus side, right? Okay, so negative a half, right, from the negative side. So this is like negative 0.6, negative 0.7, and so on. In the numerator, will that be positive or negative? Positive. What about in the, so that'll be positive. What about in that first parenthesis? Negative. What about in the second parenthesis? Negative. So the whole thing will be positive infinity. So what will it be on the other side? Negative, right. So positive over negative times negative, that'll all be positive. Like minus is positive. Okay? All right, so go ahead and do the same thing for the other one. X equals negative 3, positive 3.
Wait,
so this one is negative infinity.
Both positive and negative are positive infinity?
Huh? This one was positive, this one was negative, because it's a multiplicity of 1. So now you're going to do the same thing for x equals 3. Limit of f of x. X approaches 3 from the minus side. X approaches 3 from the plus side. So from the minus side, this is like 2.9, 2.8, 2.7, right? In the numerator, that's going to be negative. Here, this first parenthesis will be positive. This will be negative. So it'll be positive infinity. And here, negative infinity. All right? So if you put in a number,
because it's going towards the negative. It's going down.
right, it's negative infinity.
But if there's only one negative, if the bottom only had one negative sign, like not plus and then it would be the opposite.
Okay. We okay with this? Do we need to do more?
No.
I think, right? We're good. Okay. So you would have to, so here it'll be at x equals negative 1, x and x minus 4, and so on. Okay. So now let's talk about finite limits as x approaches positive or negative infinity. Huh? Wait, say it?
What's the joke? What are you doing now?
Right. So it's important to understand that infinity is not a real number, right? If there is no point, like if you can't get into a spaceship, fly somewhere and be like, I'm at infinity, right? That doesn't happen. We use it, no, he goes beyond infinity. We use infinity to describe, so we use infinity to describe the behavior of a function when we exceed finite bounds, right? So we can think about like x approaches a million, a trillion, a million trillion. But then there is a point where like we just exceed all that. Then we say as x approaches infinity. Now, that is how we describe horizontal asymptotes. So formally, y equals b, that line will be a horizontal asymptote, right? If the limit of f of x as x approaches infinity equals b. So as x approaches infinity, if the limit is a finite number, b, then y equals b is a horizontal asymptote, right? Or if the limit of f of x as x approaches negative infinity, suppose it's equal to like 7, then y equals 7 is a horizontal asymptote. All right, so take a look at this graph. Okay, this function, x over the square root of x squared plus 1. We want to find the horizontal asymptotes. We do that by finding the limit as x approaches infinity of that function. Graphically, we know that, we see that at 1, right? It is leveling off eventually, so that's a horizontal asymptote. Mathematically, right? Remember when we find limits at infinity, we basically just take the leading term over the leading term? Well, here, this would be the limit as x approaches, so we know this is 1, right? But let's see why. The limit as x approaches infinity of x over x squared, right? Now, this would be the limit as x approaches infinity of x over, this would not be x, this would be absolute value x. Like whatever comes out of here has to be positive, right? So it would be absolute value x, and then that would, for positive x values, what would that equal? So if x was like 5, what would that equal? This says at infinity, but let's test if x equals like 5, what would that equal? 1, right? That's why the limit as x approaches infinity is 1.
Why does x have to be an absolute value?
Because anything that comes out of a square root has to be a positive, right? It can't be a negative. And remember back in the day we learned even, even, odd? So if the index is even, and if this is even, and it comes out to x to the power of 1, which is odd, you need absolute values. I forgot about that, huh? Even, even, odd. It was a year and a half ago. Okay, now look at this one. The limit of f of x, now in the graph we see that this is equal to -1. But why algebraically is it -1? Because now this will still be x over the square root of x squared. Oh, this is the limit. So this is the limit as x approaches negative infinity, x over absolute value of x. Now, for negative values of x, what would that expression equal? -1. This is always 1. I mean, this is always positive. So let's say for -5, this would be -5 over 5, -1.
Yeah.
So both with the graph and with this, we're coming up with the same thing. So it could be that like this exact same question or something very similar, right, shows up on a test at some point, and you are not given the graph, you are not given a calculator, but do you see how we can find what the limit at infinity is, even though we might not even know what that function looked like, right? Okay, so now, because the limit as x approaches infinity is 1, there is a horizontal asymptote at y equals 1. Because the limit as x approaches negative infinity is -1, there is a horizontal asymptote at y equals -1. All right? This is how we know there are horizontal asymptotes. So if you told someone the horizontal asymptotes are this, and they said, justify your answer, what would you show? What part of this page would you show? The limits. You would show these. Okay?
We show the work we did with after values.
There is no need because this really is it. The rest at this point, it's just expected that you know how to do. Okay? All right. So use graphs and or tables to find all of this. Limit as at infinity, negative infinity, and then horizontal asymptotes. Okay, so turns out we could just do this like algebraically, in a similar way, right? So let's see. So for part A, we want to find the limit. This is so exciting. I love teaching this. So I want to find the limit as x approaches infinity of f of x. We are going to take the leading term with the leading term, right? At infinity, what would this look like? 2. B, limit as x approaches negative infinity, f of x, what would that be? Negative 2, right? Because it's like negative over positive. Fabulous. So now C, what are the horizontal asymptotes? Y equals 2, y equals negative 2. So A and B is the justification, C is the thing, okay? All right. This takes us to end behavior, okay? Well, what we are doing here, right? Limit as x approaches infinity, this is end behavior. But there is another thing we talk about in math, which is end behavior models. And that comes from this. Suppose you have a function, a polynomial function, right? Like this. We know what this looks like. I mean, we can figure out what it looks like in the middle, right? Like there's like an x cubed and whatever. Now, at the infinities, which is the only term here that matters? This one, the leading term, right? Because a trillion to the power of 3 has 36 zeros, but a trillion to the power of 2 has only 24 zeros. It pales in comparison, right? So whatever this graph is doing here, at the infinities, it will act like a cube root graph, okay? So the end behavior model would be y equals 4x cubed. That just says at the end behavior, at the ends, it behaves like 4x cubed. All right, so that's pretty much how we find end behavior models, is just do the limit as x approaches infinity, you know, the leading term, and whatever, okay? All right, so take a look at this. Match the function with the graph of its end behavior. So let's find end behavior models. Right? So here, okay, you have to say y equals leading term, 3x squared. Cool? Here, y equals, what is that? Negative x cubed over 2. Y equals negative x squared. Cool? Now, which of these do they match with this? So these are each the end behavior models of their respective like 1, 2, 3s. So which one does the first one match with? B and A and C. Yeah. Yes. Yeah. Oh, yeah. They go with this. Yeah. Okay. All right. So here, use a power function and find a power function end behavior model for B. Same thing, right? So then identify any horizontal asymptotes. Y equals negative 2x squared for this one, right? That's the end behavior model. All right. Horizontal asymptote, what do we think? None. No horizontal asymptote, right? Horizontal asymptote, first of all, like this is a polynomial function. This is a quadratic function. It has no horizontal asymptote. It would be if you had like a rational function. That's the end behavior model. And then for the horizontal asymptote, you say none. Because I'm asking you for two things here. Power function end behavior model and horizontal asymptotes. So here, also, remember, sophisticated, elegant math students, right? Notation. This is the function, and then this is y equals, right? Because that's not technically the function. It's just like a model. Okay. All right? Okay. So y equals what? 3. Cool. What's the horizontal asymptote then? Y equals 3. Y equals 3, right? And then if I said to justify for the horizontal asymptote, you would say the limit of f of x as x approaches infinity is 3. The limit of f of x as x approaches negative infinity, also 3. You should check both ends. Okay, because we take the leading term and the leading term, and then when the powers are the same, you just take the coefficient, the ratio of the coefficients. So for limits at infinity, you take the leading term and the leading term only. You would have factored if you were looking for vertical asymptotes, which is not what we're doing here, right? Okay, let's talk about continuity. We have talked about continuity before. We even talked about the continuity tests before in chapter 2.
Oh, chapter 2?
So a graph is continuous if basically you can draw the whole thing without taking your pencil off of your paper. Okay? Great. Now, know that for a function to be continuous, first of all, its domain does not have to be all real numbers, right? Like y equals ln of x looks like this. The domain of this is not all real numbers, but this is a continuous function because you can draw the whole thing with no gaps, right? So the two are not really the same thing. Yeah. No, because it does have a vertical asymptote, but if a function is continuous over its domain, then it's continuous.
Like if we say the domain is negative.
It's not though, because the domain is all the values of x that are not undefined for this, right? All the values of x that would give you a defined value. No, because this is not, okay, so like ln of x, it can't have domain of negative to positive infinity because ln of negative 3 does not work. That's why the domain is 0 to infinity. And then if within its domain it's always continuous, then we say it's a continuous function. Okay, now, having said that, we rarely ever talk about whether a function is continuous over its whole life. That is not really what higher math. Calculus is more about what is happening in a tiny, tiny space, right? So it's more important to talk about continuity at a point. Now, so let's talk about an interior point and an end point, okay? If you have, suppose you have a function like this, right? It starts at A, it goes to B, okay? And then if you have a point C here, that is on the interior of this domain, that's called an interior point, okay? Now, we are asking is this function continuous at point C? To say whether or not it's continuous, three things need to happen. And we did this before. It was the continuity test. Number one, the limit has to exist. So here, does the limit exist at C? Yeah. Number two, f of C has to exist. Is that true here? Number three, the limit and f of C have to be the same. Is that the same here? Yes. So that's how we know the limit, it's continuous. Now, how about at an endpoint? Okay. So suppose you want to know if this function is continuous at this endpoint. In that case, you still have to do the three things. Does f of a exist? Does the limit exist? But to find the limit at a, can we look at it from the left and the right? No. So in that case, we only do a one-sided limit. So does the limit exist from the positive side? Yes, it does. F of a exists. Are those two numbers the same? Yes, they are. So the function is continuous at that point. Okay? Okay.
What's F of C?
The y value at C. Okay. So let's just remind ourselves about some discontinuities. You have here a removable discontinuity right here, right? So the limit of f of x as x approaches 0 is 1, so that works. F of 0 is 2, it exists, but where it fails is the limit of f of x as x approaches 0 is not equal to f of 0. So that's where it fails. Okay? Because there's a hole here, but the point is at 2. So here, the limit of f of x as x approaches 0. What's that? Doesn't matter. It's D&E. So this is where this fails, right? So it already failed the first part of the continuity test. Here, the limit of f of x as x approaches 0 is also D&E. Oh, I'm sorry, it's infinity D&E. Right? So it does not, it's not a finite number. Here too it failed, right? So it's not continuous. So in this case we have, because it's going to infinity though, we have a vertical asymptote, just like we talked about on the first page. And then this is an oscillating continuity, which we already know about. Okay. I mean, discontinuity, I meant. Okay, so let's take a look at this. Find the intervals of continuity and the points of discontinuity and identify the type. Fabulous. Okay, let's factor this. X minus 2, x minus 1. So I know if I have a rational function, there's going to be some discontinuities. Before I even look at if anything cancels, there are two discontinuities at x equals 2 and x equals 1, right? So the function is continuous from negative infinity to 1, 1 to 2, 2 to infinity. Discontinuity, the points of discontinuity are x equals 1, x equals 2. And what kind of discontinuities are they? Infinite, both. Okay. Okay, yes, it's open there, but also love the questions, but raise your hand. Okay, so here we go. Where is this function not continuous? Nowhere. It's continuous everywhere. So if you're confused, ask yourself, do any x values make this undefined? And that's no, right? There is no x value that you can't plug in here. So this is continuous from negative infinity to positive infinity. Okay, here we go. ln of x minus 1. This has a shift to the right one, so you don't have to draw it, but you know, the vertical asymptote is now here, so this looks like this. Okay. Again, there are no discontinuities because the moment this function is born, right, like the moment it starts to exist to the end, it's just, I mean, it's continuous, right? It just goes continuously. So it's continuous from negative infinity to positive infinity. Oh no, oh my gosh. From 1 to infinity. Oh boy. Okay. Now here, is this continuous everywhere? No. What x value? 0. Cannot work here. 0. So why can't that work? Because this is e to the 2 over x, and then it'll be e to the 2 over 0. You can't divide by 0, right? So this is continuous from negative infinity to 0, from 0 to infinity. And even though it's e to the power of something, because, right, it's like in the denominator, right, it'll be an infinite discontinuity, right? So infinite discontinuity at x equals 0. Yeah.
But if it was x over 2,
Yeah.
But it's not a it's vertical asymptote.
Thank you for raising your hand. Did you? Yep.
It's not a vertical asymptote.
It is a vertical asymptote. Infinite discontinuity means vertical asymptote, right? Look, as this x approaches 0, 2 over x will be infinity. E to the infinity is even bigger than infinity, right? Okay. So what about here? Is this continuous everywhere? No, 0, it's not, right? So this is continuous from negative infinity to 0, 0 to infinity. And is it infinite, removable, what? Infinite discontinuity at x equals 0. Okay. Piecewise functions. Let's graph it. Okay, so let's graph this. Negative 1 to 0, right? This one. So this one is a parabola, right? Looks like that. Yeah? Okay. So, and we're just graphing from negative 1 to 0. So at negative 1, this function is how much? 0. At 0, it's 1. And then we know this is part of a parabola, so you got to make it like curved like a parabola. Then this should have been open. It does close later, yes, but you know. Okay, so then for the next one, right? At 0, it's 1, closed, so we close it. Then at 2, it's 3, and this is just a linear function. Oh, that's open as well over there. I'm just missing those open circles today, okay? Okay, at x equals 2, it's 4. At, okay, greater than 2, it's negative x. So at 2, that one is how much? Negative 2. Open. Here we go. All right? Okay. Does f of negative 1 exist? Yes. Okay, B. Does the limit at x approaches 1 from the minus side exist? 1 from the minus, yes. Trick question, I know. How about, okay, here we go. Does the limit as x approaches 2 from the positive side equal f of 2? Right, because how much is the limit? Right, and this one is 4, so no. Is f continuous at 0? Yes. Okay. How would you justify that? Yeah, the limit of f. So look, here is a more efficient way. The limit as x approaches 0. Okay, just how much is it? Just for, it's 1. How about f of 0? Also 1. So this is equal to f of 0, which is equal to 1. And that's enough of a justification. Okay? Do we need to do another piecewise function? I think we're good. Okay. This one. Okay. Find each point of discontinuity. Which of the discontinuities are removable? Which are not removable? Okay. So for this one, right, we're just going to plug in points. Okay. So at 0, so let's see, at x equals 0, right? What's the limit of f of x as x approaches 0 from the negative side? 0. What's the limit of f of x as x approaches 0 from the positive side? 6. Right, it's a jump discontinuity. So the limit of f of x as x approaches 0 does not exist. This one is jump for sure. Okay, what about at x equals 3? As x approaches 3 from the negative side. Yeah, this is 6. Also 6. So this is continuous, right? The limit of f of x as x approaches 3 equals f of 3 equals 6. All right? Okay. One more thing I wanted to do is the following. What I wanted to go over was this one. I wanted to go over this function. E.
What page is it?
The previous page that we just did. E. Right? This is the one I wanted to go over. Right? So we have y. Okay. So we have y equals absolute value of x over x. Right? And we want to know. Oh. Boy. I did this wrong. Oh my gosh.
It's been a long day.
Oh my gosh. When we put 0, so I don't know what I was thinking here. So when you put 0, okay, you get 0 over 0, which is indeterminate, right? It's indeterminate. So let's think about what happens here, right? So we don't know what happens at 0, but let's plug in 1. Now, we are used to function notation, right? Like f of 1, f of 2, right? This function's name is y. So we can also write, by the way, y of 1. Y of 1 is 1 over 1, right? Which is 1. What's y of 2? 1. What's y over 3? Y of 3? 1. So, right? Okay. What's y of negative 1? Negative 1. What's y of negative 2? What's y of negative 3? Right here.
But it just doesn't exist.
Correct. It does not. But now, how about at x equals a half? Still 1. Negative half? Still 1. It only doesn't exist here, but look at this. It looks like this. So this is a jump discontinuity. Okay? I apologize. I really don't know what I was thinking over there. Oh my gosh. What a rookie mistake that was. Okay? But look though, you know what? Maybe it's a blessing that happened, right? 0 over 0, right, is indeterminate. Don't go judging a book by its cover like that, right? 0 over 0 is indeterminate. You just never know, right? This was a jump discontinuity. Okay, we'll stop here and you have a handout.
Which part is not
Which
which
Press start.